am delighted to introduce John Arenberg from Northrop Grumman. He is the Chief Mission Architect in the Science and Robotic Exploration Division. So yesterday he gave a talk on the James Webb Space Telescope, which we all know and love, which he helped build. And now we're going to learn about the importance of communication. So John works with scientists and engineers, which communication is essential for that. So take it away, John.
Okay. Thank you very much. So thank you for coming to hear me talk on communication. And I put the parenthetical on there because when I sent the abstract, that was on the original title. And so I left it there for truth in advertising. So to give you an idea where we're going, for those of you that may recognize this, this is one of the first light images from James Webb, and the secret power that made this image possible was the communication amongst a large team to get everything from export-import contracts, funding from Congress, and the occasional technical detail taken care of. So let's begin. That's the preface. So let's start off with the first most fundamental question. Why am I here talking about communication? I'm an engineer. I'm the dyed-in-the-wool engineer. On certain days, maybe even a scientist, but definitely an engineer. And why am I here talking about communication? You would expect that from somebody from a different academic background. And fundamentally, the reason is it's important. It is critically important. So we'll emphasize that with another slide that says really important. And the reason that this is important is also very simple. It even says that, right? Okay. And here it is. Ready for it? You're all waiting to see the next. What could ever be the reason? It is as simple as this. Advancing science takes hardware. We need to use science to make observations. To build that hardware takes people. And let's have a little fun by the transitive property of few graphs. Clearly, advancing science takes people. This is doubly true for an observationally driven science. Astronomy, as an observational science, as an example, demands increasingly sensitive tools to drive advancement. So I did tell you I was an engineer. So here's a plot with some data on it. And this is the largest telescope from the dawn of the telescopic era. You will note that this is a logarithmic scale. Telescopes have gotten a lot bigger since Galileo made one. And if we zoom in on the most relevant, basically half century, you can see these are trend lines. These are not fits. This is John taking out a crayon and scratching it on the plot. But what you see, that white trend line is the trend line for the largest telescopes on the ground. Purple space visible in IR. So if you remember from the previous slide, that slope is significantly higher than it has been over the last few centuries. Okay. Basically, all the easy stuff has been done. Now, when I mean easy, I'm talking about tabletop instruments that are within the span of a single person or a small team, a professor with a couple of grad students to build it. This was especially true. I mean, Galileo built his own telescope even up as late as Herschel even into the early 20th century, even some of the largest telescopes on the planet. There was very little instrumentation other than your eyeball and a sketch pad for most of the 19th century. Photography came in fairly late, still within the span of a small team. To move the field along, we need new systems, right? We talked about this yesterday, I believe. No one's going to pay billions of dollars to reduce the error bar on a measurement by 1% or 2%. Want fundamental leaps in performance, new things, great advancements. I mean, the difference between the 10-meter Keck telescope and the 40-meter that's coming will be ground shaking, pun intended. And doing new things is extra hard. This is because you're breaking into a new regime of size and new behaviors and larger, more complex systems, and it takes lots of people. So here's a prototype, one of those new complex systems, and I picked this picture in particular because this was the day we put the telescope and the instruments on called the space vehicle. So over here is the spacecraft and the sun shield, and we had to pick it up and connect it, and you can see a small subset of the people involved. And when you do it, I can't get away without showing this picture again. And you are successful, you get noticed and rewarded. And of course, this is a large team. But I would note that in this team, there are engineers, there are communications professionals, there's finance people, odd program manager. In there was a broad, diverse team that went. So advancing science really takes people with different skills and outlooks. This is a fundamental property of developing a new complicated system, whether it's an instrument for the ground, it's a new laboratory, it's standing up a new center, it's building habitable worlds, or any of the other things that we're involved in. So just a few of the job types involved in the development of Webb and some of the other missions I've been involved. Certainly there's a scientist or two involved, right? Both on the customer side and on the performer side, and even a few driving by to offer opinions as reviewers and members of the public. Engineers, managers, we buy parts for the spacecraft and get instruments from overseas. So even when we get a contributed instrument, it's got to be shipped, and the folks at the airport want to inspect it. So you don't want a delicate, super clean instrument being taken apart because they're looking for contraband. So somebody's got to go work with customs to say, no, this is not X. It's really a science instrument. Trust me, and you've got to go work with this embassy and that embassy and licenses, and that's a whole adventure all in its own. And trust me, you want an expert, right? But you also want them to understand that this is a contamination sensitive or a delicate instrument. So no, don't open it up. Go ask the customs people what they want to inspect, and let's get them what they want. Gotta buy stuff. I mean, I'm sure people with labs here have dealt with procurement. Everybody's favorite people, but we buy lots of things. If we go back to the picture, here. If you look at the yellow equipment, these other pieces of equipment, what we call ground support equipment, to make James Webb one configured item of space hardware, there were 562 pieces of configured ground support equipment. We had to buy all those pieces, had to put them together. It took a lot of buying. It had to be done on time. Parts had to be the right thing, They had to show up. It required that kind of expertise. Clean room needed to be cleaned, need janitorial support, needed to tell the public. And we needed admins, which used to be called secretaries, almost the most important people on the program. They got everybody badged and got them in for reviews, made sure there was lunch and coffee at the meetings, not a trivial undertaking at all. And we had lots of foreign visitors, so we had to deal with visitor control and security as an example. And we even needed lawyers. We even had a staff meeting. Every time we went to the program manager staff meeting, there was our program council. So it takes a wide variety of people. It's worth noting that James Webb is the result of, on the rough order of 100 million people hours of effort. They were not all the same people. They were not all the same age. They did not live in the same time zone, same country, same space agency. You get the idea, right? Once you get beyond that group of 3 or 4 or 5, all of a sudden, culture, experience, time zone, all these kinds of things matter. All these people usually spoke some kind of common vocabulary, some kind of common, call it language, usually English. But, if you remember one of my favorite, Winston Churchill quotes, that the Americans and the British were a single people divided by a common language. Not quite true, because the English spell funny, so it's not recognized as proper American, but you get the idea, right? These people, as we have outlined, are groups of different cultures and outlooks. Scientists will look at a problem one way. We just had that discussion earlier about the long wave cutoff on habitable worlds. The scientists want to push it longer, something I completely support as an engineer. And there are engineers at the top of the mission that are terribly concerned that by getting the system cold enough, it's going to contaminate and ruin the ultraviolet end. So they've said, no, you can't have that. I'm of yet a different outlook, that I'm not ready to say no yet, and we should explore the options, right? I don't believe there's only one way to keep a mirror clean, right? So communicating those ideas, getting them out on the table, saying, okay, today's the day we're going to have our long wave cutoff fight, and everybody brings their tools to the speak off, and we go at it and make a decision. So even though these folks will use a common set of words to think everybody's speaking the same language at a conceptual level is a misconception, right? People fundamentally look at the world differently based on their outlook, their professional position. And in fact, a scientist who's the project scientist versus an instrument scientist versus a general observer may even have, I'll call them subcultural differences in how to look at a problem or how to look at a solution. So the only thing you can say to that, given the fact that we have outlined that science needs to do these big complicated things, to do those big complicated things, you need these giant enormous teams. And even though they appear to speak together, they don't necessarily communicate. So there's only really one word that sums up this situation, and that's yikes. Oh my God, this is a fundamental problem to advancing science, which is what we're all dedicated to do. That's how I pay the mortgage. That's how you all pay the mortgage. So we've got to find a way to be successful. So I want to figure out a way to do something about it. So what I'd like to do is give you some tools here, and we're going to have a little fun, because I'm going to Actually, as you will see, there's a number of examples. I'm going to tell you a story. Not a made-up story, but a real story that has happened in the development of one of the large missions that I have worked on as an example to improve communications across these steps. So now we've outlined the problem. So we have a fundamental challenge. We all want to move our intellectual achievement, our scientific advancement down the field and leave the field in a better place than when we joined it. That requires observation. Even on the theory side, as we were talking earlier this morning with the enormously complex models, even the students are developing. You need to find a common way to interface those models and get them to work together to glean a higher level truth. So I would argue even on the theory or the simulation side, this applies, but all of these stories relate to hardware. Some of them are quite fun, I hope. So first step in solving a problem is recognizing there's one. There's lots of quotes. The first one I found was related to the HBO series, The Newsroom, which I have never seen, but I've certainly said this, and it's certainly true. So we have this fundamental problem or challenge to communication. So the first thing you need to do is recognize that is an issue. Okay, so we need to face this challenge and know and recognize the obstacles to communication. So there's a couple of them, at least as I've outlined them. You can Google effective communication, and there's a lot of other ones that you will find there. I don't think they necessarily apply because it's workplace hostility and all kinds of other stuff. I'm talking about well-behaved, well-meaning scientists, engineers, professionals that you don't have to send to HR for, because that's a whole different gambit, and I'm absolutely not expert on that. So George Bernard Shaw was credited with the quote, "The biggest problem with communication is the illusion that it has been accomplished." If you actually go look this up, this may not be a proper quote, even though it's completely correct. Some authors will attribute it to some business publication in the 1950s. I say that because I'm at a university and somebody's going to check my quotes, my epigram, but regardless, it is a fundamental statement, right? You cannot simply assume that communication has happened. So again, we want to remind ourselves that we not assume that because you've spoken or heaven forbid sent an email that message has been absorbed and acted on. Right? There's lots of examples of particularly some of my junior engineers send an email and assume that their warning of impending doom was understood and acted on, and they won't mention it again. We corrected that quickly, right? But this is a classic example. So let's start with our first story. So before I began to work on James Webb, I worked on an X-ray mission called AXAF, which is now called Chandra. And most of my day job was to work on the ground test. So this telescope collects X-rays from the sky, and one of its fundamental scientific requirements was absolute calibration, absolute radiometric calibration. What that means is when you measure a count rate, the number of photons that you collect, and there are not a lot of them. One of the PIs said, "We know and love every photon, especially we name one, we give them all unique names because they grip in one at a time at the rate of about 1 a second. So they can be named by where they fall on the given focal plane and the time they arrive. And that's completely unique." So they're scarce. And so to establish how bright the luminous the objects are in the sky, you need to know that transfer function. It's how many are lost in the telescope, getting from the input to the focal plane. And so designing that test involved 15 or 16 organizations, all going to a NASA test facility, all bringing equipment, computers, procedures that all had to go together. So we had to line things up, and we would use a theodolite from, or an optical source from one, and a lens from another, and it had to go on a detector that went on a third that integrated into the facility. And we had a lot of interfaces, hundreds of interfaces. And this was a particularly close team. We met every month for 7 years to get ready for this test. And one day, we were having our usual discussions, monthly discussions, and somebody brought up a problem with the AAS. Well, they started describing the problem, and somebody else said, "Oh my God, that changes everything." And this, bless you, and this particular conversation rapidly went out of control. My job is to herd these cats. Right? I happen to have a substantial herd at home. I know how to do that. And my little voice said, something's not right. You know, you guys are talking past the conversation, doesn't make sense. And people got more and more excited. And this was a group of people that we would all fly to Huntsville. So everybody was away from home. And we would routinely, 20 or 30 of us, all go to dinner, or all go play pool, or all go drink beer together. Every month after month. We could name each other's kids. Very close group. Still close, 30 years after we did it. But this is now descending into chaos, and people are, I'm not redoing this, blah, 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 and they're getting mad. And I said, stop. Okay. What is the AAS? Right? And they said the angular alignment sensor. And then you could hear the 6 other people involved doing the dope slap because they thought it meant something else. I said, okay, everybody take out your documents, because this was an era before laptops, and we took out a clean piece of plastic, put it on the projector, and went through from 1A acronyms to triple Z, and found out where we had degenerate acronyms that meant different things. And we deconflicted them. And after that, we said, okay, when you write a document, next meeting, we're going to have the new acronym discussion so that we don't have this problem. So again, everybody thought they were communicating effectively, but they were doing it wrong because there was something implied. So that's story one. The other is something that is called the curse of knowledge. Okay, and fundamentally, this is the assumption that other folks know what you know, and so you immediately go into expert mode to explain. So this can be represented by this Venn diagram. And depending on how afflicted you are, you may think this area of common intersection includes some of all knowledge or everything that you know. But assuming this is again one of these fundamental challenges, you shouldn't do that, particularly on a big team, and we'll talk about why in just a moment. In fact, I would advocate that you should assume that there's no overlap, that overlap is exactly the null set. The reason for that, again, is relatively straightforward. Teams that work on new complex systems such as web typically don't have the luxury of having redundancy of skills. That is, when I had my design integration meeting where we would talk about the observatory design, I had one thermal engineer, thermal lead. I had one mechanical designer. I had one structural analyst. I had one contamination control guy. I had one guy working interfaces. I didn't have 12 people in the hopes that one of them understood me and would translate. Right? So you got to be very careful, because typically you don't have this kind of backstop of hopefully communicating to one of the diverse redundant people in this other tribe, if you will, because they're not there. So you just should assume, particularly the more expert the people get, the more siloed they are, because this is typical. So this is the second story time coming up. So how many of you were at the James Webb discussion yesterday? Okay, this is a trick question. What was your favorite part of the talk? Now there's a hint right here, guys. So, okay. So what was your favorite part of the talk? Good, correct answer. Even if you don't believe it, thank you very much. He'll be very happy when I call home tonight, because he likes to know how his fans are doing. Okay, so I'm now going to tell the story from a different perspective. One of my jobs as the design leader and eventually chief engineer was to go out and talk to audiences. And these audiences ranged literally from retired government ministers. I think I briefed the foreign minister of Japan, several ambassadors, 3 Nobel Prize winners, and elementary schools. And I needed to explain the fundamental workings. And so one of my early assignments was a request to go to an elementary school and explain James Webb to a bunch of 3rd graders. I also had to explain it to a lot of folks in the press, but we're covering whatever, and I couldn't assume that they all had physics degrees. So again, I wanted to explain the infrared and the cold, because it's not obvious. It's not simply put. So again, set up the story. Want things quiet so we can see the stars. This is a visual cue. Most people can get that concept. That leads us to the black body, and then you snap on, and then of course the fact that this is the constellation Orion is not an accident, but you don't know that when you hear it. Okay, and here's Orion sitting here, right? And at this point, my audience will bifurcate. They're the experts that already know the answer. I'm not talking to them. I don't want to lose them. I want to entertain them, right? So then I say silly stuff like how handsome he is and all of that to keep them entertained, because they will remember crazy chief engineers talking about his catch. He's talking about the black body. Trust me, they remember it. And then there's all the folks that don't know it. So again, telling it in an accessible story. Here he goes. You continue along the lines, and as you can tell, I have a reasonably good sense of humor. So we remind everybody how handsome he is, regardless of the wavelength. That always works. I've even told that joke in Spanish, and it worked. I did that to check to make sure I was communicating properly. And then you conclude with the fundamental message, right? The reason Webb is told is because it has to be, because it's so sensitive, needs to be so sensitive to advance. Okay. Now, I could have shown this, right? I could have said, oh, here's the Planck function, and look at the value of the argument here, right? But I don't think that's necessarily better. Again, the people that already know the answer don't need to see the equation. They don't need to see the curve. They know the answer, right? And then the fact that this isn't actually complete, right? This equation needs to be modified with some terms up here. And then if I wanted to go down the rat hole and lose everybody, because I did the first time I tried to describe this in detail, even to experts, right? Because we're dealing with concern about stray light, and we have to worry about the contamination. We have to worry about spectral directional emissivity. And in fact, there's different emissivity that governs the thermal. So you can go down a complete rabbit hole, whatever you want to call it, talking about how I did this calculation. But fundamentally, that's too much detail. So this is actually an early version of the slide. I would argue that the ones that just have the big cat pictures are more effective. And the people that want to dig in, and keep in mind, we had a 2-day discussion of that term alone. I got all the experts and we needed to have an agreement on how we were going to handle the impacts of contamination, both molecular and particulate on delicate thermal optic surfaces. Sunshield, this is the mirror. So here's a good question. When I say contamination, does everybody know what I'm talking about? Maybe you're all nodding because you don't want to be the one who sticks up your hand and says, I don't know. Okay, so the way I define contamination is material on a surface that is not part of the design. This is dust, this is molecules that accumulate out of the air. And at best, on the best day, contamination is benign, never helps. Because quite frankly, if it helped the design, we would have incorporated those properties in the design, but usually it's bad. So we had a whole separate discussion of these effects amongst experts, and even then it was challenging to describe the analysis that I did and why I thought it was correct. So particularly when you are trying to be understood clearly, you want to speak as plainly and as simply as possible. Fundamental concepts common across your group of colleagues, be they scientists, be they engineers, export control people, lawyers, the occasional manager. And you have to be very careful with the lawyers. Want to be very careful to avoid jargon. There's any number of terms, common terms of art. So when an astronomer uses the word feedback, this took me years to figure out. It's very different than when an engineer says it. Very different loop. It's a very different physical process. Yet I go to meetings and people use the same word to mean two different things. You want to do your best to avoid idiomatic expressions. That's a lot of fancy words for your own version of names and ideas and expressions. So James Webb, we had lots and lots of pieces. They all, especially if we talked about them a lot, got colloquial names. It was important to identify the pieces, and then we just had to make sure those colloquial names got used over and over again. So there's bibs and frills, and one of my favorites is the poofy sleeve and the shower curtain. And then once you use that and made sure it was clear, we have lots of slides that says, this is the shower curtain. It's actually a deployable shield that goes around the refrigerant tube that deploys and connects the cryo cooler, which lives in the spacecraft, to the cold instrument. And it interrupts heat from loading this cryogenic interface. It also prevents ice from accumulating, which changes the emissivity, all of which are bad. We certainly want to avoid acronyms until you're absolutely sure you're clear. Remember the saga of the AAS? No, we took it out, we laid it out. What I didn't tell you is we found 15 or 20 more. Some of which were, represented. We had a lot of A's, for example, because we were at that point AXAF. So there was the AXAF this and the AXAF that, and the A's took up 2 slides. Once we got it closed up, I'm very happy to report that when everybody showed up with all of their equipment, all of those hundreds of interfaces, everything fit together and worked the first time. Because we had worked it all through and we were very clear about what we had done. And you want to understand the people you're talking to so that you can speak at the right level, right? If I was going to go to a conference of thermal engineers to describe the architecture and verification of James Webb Space Telescope, Orion's not going to be at the top of my list. He will show up, trust me, somewhere. He'll peek out and ask a question or do something. I would use the language and the terms appropriate to that audience. But in general, I address more general, wider audiences that may or may not have a deep background in applied physics, or some people I know understand and know what the black body curve is, the Planck function. They just haven't dealt with it enough to understand its implication on the system. So I help them to understand it in that way. Time for another story. So this is another story ripped from the pages of the XRCF files. The XRCF was the X-ray calibration facility. This was in Huntsville, Alabama. Now, keep in mind that the mirror we were building for Chandra, now AXAF, now Chandra, which has been flying for almost 26 years, was hundreds of millions of dollars in development. Extremely valuable, literal one-of-a-kind item. So every time we picked it up, which of course you did with the crane, there was extensive checking with a test lift so that the crane wasn't going to fall down. And everything all along was very careful. So one of the things NASA wanted to do was record every command sent during the test that went on from us. So that if anything happened, we knew what. So they had brought along as part of the calibration facility this thing called the Master Control Computer, the MCC. And it had a protocol for communicating. Right? So we're getting ready for one of our monthly meetings. And an email, which was relatively new at the time, went out with an attachment. And for those of you that remember the early days of email with UU encoding and pulling out attachments, when you sent out documents, it was an adventure as to whether your compatriots could download it. So after several people couldn't, I made copies and FedEx the document that I was able to print, because that's the way we backed it up in those days. And all of a sudden the phone starts ringing off the hook. People are losing their minds over this protocol. NASA's making us rewrite this and that, and I got to rewrite my software, and people are just coming unglued. I said, okay, I know what's number one on our agenda. We're going to talk about this. So we everybody gets to Huntsville, we get to the conference room, and I have no control over the room. People are just beside themselves, right? I did this for my software, and it's on and on and on. This goes on for quite some time. Like I said, literally probably 3 hours. It's not good. I've lost control. I got to do something. So fortunately, or unfortunately, the cafeteria at Marshall Space Flight Center runs out of food quickly. So I said, okay, it's 11:15. If we want to get anything to eat, we better go get some food. Okay, two rules, everybody's got to come back on time and nobody can talk about this. And I said, when we come back from lunch, we're gonna solve it. Turned off the projector and I left the room. As I'm walking over to get lunch, one of my colleagues says, what are you gonna do? I said, I don't know, I haven't figured it out yet. And I had lunch and didn't talk about it, and then the idea came to me, and we came back. And it took the program off, and I said, okay, you're the 8 or 9 people that are most affected. Everybody get away from the table. 8 or 9 people, I made them sit at the table. And I found something, an eraser, a notebook or something. And I said, this is the talking influence. Only this person and me can talk. I gave it to the first person. And I stood up by the projector, which was off, but I had put a blank piece of plastic on there. And I had the first person describe the problem. Every time they got to a fancy buzzword, I wrote it down. Protocol, TCP/IP, address, header, whatever it was. No hard and fast rule. All the way to the end. Let everybody go. Walked over and Marshall, it didn't have laser pointers. They had these really impressive and wonderful pointers, right? Stick, 3.5 feet long, 1 inch wide. I went over and I picked it up. And I turned on the projector and I went to the first guy, who not incidentally, not by accident, was the largest of the 9, quite large. My aspect ratio, but like 1.5 feet taller, so really big guy. And a good sport. And I said, okay, Tim, now I want you to restate the problem, but you may not use any word that's projected on the screen. And if you do, I'll help you out because I'm going to hit you with this stick. I wasn't going to hit him, but it got everybody calmed down and they thought about it. And I said, I'll give you a few seconds. And by the time we got to the third person, which included the guy from NASA defining the problem went away. It turned out all they wanted to do was attach a small header, which we would now call metadata, to all of the messages so they could be sorted. They weren't rewriting the TCP/IP, the fundamental means of Ethernet communication, none of that. They just wanted to attach this little bit of data. And we had all gotten our shoelaces tied together because we had read one word that meant different things to different people and then overinterpreted instead of just saying, this really shouldn't be that hard. Why do I think it's hard? So one of the ways I have found that has worked time and time again, and I probably got it from my father when I was a little boy, who liked to make me exercise my vocabulary and point at things, tell him where things were without pointing, and all of those kinds of exercises, is if you think there's a chance that you were misunderstood, get your partner to repeat what you told. So frequently when I'm in a big room and half the time the acoustics aren't bad and I'm answering questions, I will repeat the question, not only so people that don't have the microphone can hear it, but so that I can understand it. Because I used to go to a conference there and they were scrupulous about recording questions and answers. And they would have put at the end of your conference paper. And occasionally I would look up my own and I would see the question asked and I would read my answer and I would go, I got to stop drinking before I present, because I was answering a totally different, I didn't hear the question. Didn't answer what the questioner asked. And so I have made that mistake multiple times. I don't want you to make it. I want you to make a new mistake. But have them repeat. And remember the MCC trick. Try using different words. Try it. Might work. So this one of my most fun stories. So we spent a lot of time with our program managers on James Webb, and they, were great guys and very, very gifted engineers and managers. But the two gentlemen that were our program manager and our deputy were not physicists, right? Communications and electronics engineers that had a very different view of development. When you're developing an electronics box, you design the circuit. And if you can buy the parts, you're almost certain that it's going to work as intended, right? Very rarely does a resistor not behave like a resistor should, or an integrated circuit, or an FPGA, or any of the other components that go on a board. So this whole idea of an applied physics development, which is what James Webb was, and the fact that we weren't completely certain of the physics, but we didn't know all of the interactions and all of the values, was culturally new to them. So as the design progressed, and they got comfortable in their roles, our program manager, Scott, really dealt with our upper management, Congress, NASA, et cetera. And this gentleman named Gus really ran the program day to day. And he had a weekly meeting of technical problems that needed management's attention. Well, at this point, I've been on the program a long time. I had started to get the idea that I have to be very careful when talking to folks about detailed design. And we had a particular challenge with the long wave stray light. So at 20 microns, there's a specification for how much noise, how much stray light could come from the telescope and get to the detector. Okay, first of all, it was in weird units. It was the Megajansky's per steradian, which is not watts per steradian. It's a slightly different method. And so even using the units was not clear. So we were having a challenge, and what I wanted was management's attention to focus on the problem and get to the root of the problem. We have a problem in design, we have a problem in analysis, we have a problem in prediction, we have a problem in any of the combinations. And what I needed was license to go off and do it and take a few people out of their daily work and add something else, more thermal runs and some other things. So I had to go present this problem to Deputy Program Manager Gus. Like I said, very clever person, but an electrical engineer, used boxes. And so I also knew that he had a pretty good sense of humor. So I went and I prepared a talk not unlike Story Time with the Chief Engineer's Cat. It was a little bit more sophisticated than that. But the title page that I left up on the screen for quite some time was entitled "Hot Mirrors Are Bad." And said, because this was all about problems. So if you were on the agenda, he didn't have to ask, is there an issue? We started with what was the issue. And when he saw that written, because it was very different than the other titles, right? The problem with part number XYZ, or, inrush current over blah, blah, blah on this box or that box. And the first question out of his mouth was, "You wrote that title for me?" And I said, "Yes, sir." Right? And I went through and I described the problem very, very qualitatively. And very quickly he said, "Okay, I understand, you can go off and do it." And he said, "Well, why did you do this?" And I said, "Well, Gus, I've now worked for you for 3 or 4 years. I know you trust me, or at least I hope you trust me. And I wanted to communicate effectively and get your agreement and not give you a physics lecture." And he appreciated that. And then I flipped to the backup and I had 25 pages. And I said, "But if you want one, I'm ready to give it to you." Right? And he quickly agreed and said, "Here, you can take an extra couple of hours and come back when it's finished. Anything to avoid." Okay, so fast forward. Gus about to retire. Okay, and so since I saw him every day with problems, I brought him two retirement gifts. The first one was a second bottle of baby aspirin. Because the first time I came with a problem, it was so bad, we were, you know, very worried about the performance of the telescope. I said, Gus, you can't die. I can't solve the problem and train another program manager. So if you feel a heart attack coming on, here's your baby aspirin. Okay, it'll last you long enough to get my answer, and then we'll get you an ambulance. And again, very good sense of humor. He kind of got it that we were going to work as a team. And then I gave him a framed copy of the title page, Hot Mirrors Are Bad, right? Which he then explained to his wife, who thought I was a nut, but that's okay. And so the point here is to really understand your audience, know who you're talking to or who you want to talk to. Think about the outcome of it and speaking effectively. We're gonna have another story here. Okay, I'm gonna let you all absorb this, and then I'm gonna let you all come to the wrong answer, and then I'm gonna tell you what actually happened. Okay. No, I did not go out and pick a fight with John Mather. I was asked to pick a fight with John Mather because one of the projects that we worked on as part of our work on web, as part of our corporate responsibility, was preparing a documentary, a 40-minute movie that was to go into school classrooms, talk about not only the telescope, but the people building it and STEM careers and all of that. And what the movie maker wanted to do was to set up a technical debate that then got settled by calculation. So he came to me after 2 days of interviews and he said, do you mind if I set up a scene in the movie where you and John Mather have a disagreement? I said, oh, I'm going to lose, but that's fine, right? It's supposed to happen. And the question was, is James Webb sensitive enough to see a bumblebee on the moon? Okay, so if you ever find this movie, it's called Into the Unknown. I actually do the calculation on a whiteboard, and it took, I don't know, 2 minutes and 30 seconds. But the movie maker didn't want to go in slow motion, so he actually speeds it up, so it takes about 40 seconds. It's very entertaining. Right, I'm writing really fast and erasing stuff. And basically, this was the movie maker's example of how a technical dispute gets answered. Make a question, come up with a means of adjudicating it, you follow it through to the end, and then we both conclude that you can see it if, of course, if the bumblebee is not wearing a spacesuit and it stays very still, right? So there's a few other elements to the story that again make it entertaining, but there's a fundamental message, right? And that message to us is to essentially find this common language for coming to an agreement, for settling a dispute, a difference, a means of approaching a problem. So it can be in words. The front copy of a paper I wrote. In this case, I'm addressing how to make flagships, large observatories less expensive. A lot of people didn't like it, but I wrote it down, and now they got something to throw darts at. You can also explain a complicated system by use of an image. This is a little bit small, but this is a picture of how the aspect camera works on the Chandra Observatory. So essentially, how we register the focal plane on the sky to know where the photon comes from on the celestial sphere to assemble those high resolution images. And then lastly, this is actually a page out of my logbook where I'm arguing with myself about a jitter requirement on a telescope. I don't want you to check my math. It's really an example. And this is the way I think. So words, pictures, equations. Again, the big picture here. If you remember the other inventor of the calculus, Leibniz, right? He went into understanding and defining the calculus for this pure philosophical language, right? He went into math and calculus as a way to adjudicate disagreements among philosophers. I think that's what he called it. Remember that in the old days, physics was called natural philosophy. So philosophers were really scientists and engineers, even though the term engineer wouldn't be used for another 200 years. Okay. So again, finding and mastering these tools, whatever you choose, however it fits your personality, and whatever is effective with your audience. Always amazed when I write down something like this and give it to a colleague, their eyes glaze over, and how many of them are not necessarily as mathematically inclined as I am, but that just means I have to find a different way to talk to them. Brings us to the end, so I want to summarize. We started off the talk by establishing that advancement takes new observations, new results, new ideas. These observations take hard work. Remember all the easy stuff that's been done? That is very rarely can you get a huge NASA grant or a huge grant for an instrument that 2 or 3 people can put together. So it requires a team. A team frequently extends well beyond the immediate science and engineering team. So you need to communicate across disciplines. To do that effectively, you have to recognize that it takes deliberate effort, maybe even over effort to do that. And we talked about some of the fundamental tools, recognizing that everybody doesn't have overlapping specialties. In fact, you're safer to assume that you have nothing in common except maybe some basic cultural rules. Speak plainly, speak as simple as you can. Use simple words. Don't use words that potentially have multiple meanings. I have a whole list of very entertaining homonyms. So if you're going off and making optics, there's a tool called a mandrel. It's also a monkey named a mandrel. Now, they're not spelled the same, but they sound the same way. And I remember sitting in a meeting and I said, we need to go out and buy some mandrels. And my program manager leaned over and she said, what are you buying monkeys for? She didn't understand how we made. So that's one of my favorite stories. I remind her of that all the time. But there are lots of other words that are spelled and sound the same way and mean different things to different people. So you should go and look for those and try to avoid them. Maybe even have a poster on the wall that says we don't use these words unless you know what they mean. Again, speak effectively, know your audience. Remember when I went to go see Gus. And there's no rule against having a little fun with it. Right? Try to establish and understand and use and forge a common language. Right. And so if you do that, you can make the next great leap and produce pictures and images like this that not only add to our knowledge and our understanding of the universe, but inspire the next generation of scientists, engineers, administrators, secretaries, export control people to take that next great leap. So with that, I'll finish. I'll thank you for your kind attention. Take any questions.